Hello all, we are discussing applications of resonance. We completed basic nature of amines. We did few examples also. Okay, let us continue basic nature of amines based on the resonance effect. Okay. Overall basic nature. See, aliphatic amines are more basic. This is general comparison. Aliphatic amines are more basic than aromatic amines. Aromatic amines are more basic than amides. Okay, this is overall comparison. So when you have aliphatic amine, that will be more basic than aromatic and amides. Okay, let us see how to identify aliphatic amine. In aliphatic amine, nitrogen is not connected directly to benzene ring. For example, look at this. This is considered as aliphatic because this is not benzene ring, and aromatic means benzene ring is present. When benzene ring is directly connected to nitrogen, that is called as aromatic amine, or nitrogen is directly connected to benzene ring, that is called as aromatic. Okay, amides, you know amides general formula are C double bond O NH2. Amides. Okay, amides are least basic compared to aromatic, and aromatic are least basic compared to aliphatic. Okay, let us see one question on this. Okay, right, just a second. This is acetamide, amide. Look at this question. Which is more basic amine? First of all, select which is aromatic. First one is aromatic because nitrogen is directly connected to benzene. This is aromatic. This is amide. Amide is least basic. Okay, we can eliminate this. This is aliphatic. This is also aliphatic. Okay, both are aliphatic only, but which is 2 degree amine? This is 2 degree amine, right? 2 degree amine. This is 1 degree. Both are aliphatic. Both will be more basic. But if you compare these two, which is more basic? D is more basic because this is 2 degree amine. Got it? Right. So what is overall basic nature? D greater than, B greater than, A greater than C. C is least basic. Why? Because C is amide. Amides are least basic. Clear? Right. Look at this another question. Another example. This is very important example. This is pyrrole. Pyridine. Aniline. Pyrrole, pyridine and aniline. Pyrrole, pyridine and aniline. See, here lone pair participate in the resonance. So tendency to donate electron pair decreases, right? So this will be less basic. In pyridine, this lone pair do not participate in the resonance. So tendency to donate for proton is more. So this is more basic compared to all. In aniline, nitrogen lone pair enter into the resonance. But compared to pyrrole, Here extent of resonance is less. Okay, so what is overall basic nature here? B greater than C greater than A. Okay, right. Let us see next electron displacement effect, hyperconjugation. 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 We know inductive effect and we know resonance effect definitions. What is hyperconjugation? Hyperconjugation. Displacement of carbon hydrogen sigma bonded electrons is called as hyperconjugation. Displacement of carbon hydrogen sigma bonded electrons is called as hyperconjugation. Generally it is represented with H, hyperconjugation. Okay, plus H, positive hyperconjugation. Okay, clear? Let us understand the definition. Displacement of carbon hydrogen sigma bonded electrons is called as hyperconjugation. Why carbon hydrogen sigma bonded electrons will shift towards electron deficient site or towards carbocation? Let us see. We know carbocations are electron deficient species, right? This carbon, this is electron deficient. Once look at this, it is having one methyl group. Okay, methyl group is connected in the alpha position. This is alpha position. Carbocation and alpha position beta like that. Okay, the carbon which is next to carbocation, see this is carbocation, is called as alpha carbon, and hydrogens present on that alpha carbon are called alpha hydrogens. Okay, right. I am expanding the structure. Look at this. We know carbocations are electron deficient. Right, they need 2 electrons to complete octet. Clear? See, to complete octet configuration, this carbon hydrogen sigma bonded electrons will shift like this. Okay, like this. This phenomenon, shifting of carbon hydrogen sigma bonded electrons towards electron deficient site, towards carbocation, is called as hyperconjugation. Why carbon hydrogen sigma bonded electrons are shifting? Because this is electron deficient. The electron deficient. That's why these carbon hydrogen sigma bonded electrons are shifting. After shifting, what happens? Look at this. After shifting, see, one new bond is coming now, so here we will get double bond, and this positive will become neutral. Why? Because bond is coming towards this carbon. Bond means electron only. Electron. Bond contains 2 electrons now. So positive and electrons are coming. Electron means negative. So neutralization takes place. That's why I removed positive charge here. And carbon is losing the electron now here. Why? See, in this bond 2 electrons are present. 1 electron belongs to carbon, 1 electron belongs to hydrogen. See, hydrogen is losing its electron. This electron is going towards this. That's why hydrogen will get a positive charge. Clear? So after shifting this carbon hydrogen sigma bonded electrons, we'll get this structure like this. Clear? Okay. Condition for hyperconjugation. Condition for hyperconjugation. Presence of at least one alpha hydrogen. Presence of at least one alpha hydrogen is the condition for hyperconjugation. Clear? Let us see. One small question. In which of the following in which of the following HC hyperconjugation is absent? In which of the following hyperconjugation is absent? First select alpha carbon. Which is alpha carbon? Underline alpha carbon. This is alpha carbon. What is alpha carbon? Carbon which is directly connected to carbocation, carbon with positive, is called alpha carbon. Alpha carbon. See, this is alpha carbon. This carbon is directly connected to carbon with positive. So this is alpha carbon. I am underlining alpha carbons. Alpha carbon, alpha carbon. This is alpha carbon. What is the condition for hyperconjugation? Presence of at least one alpha hydrogen. In this, how many alpha hydrogens are present? See, one alpha carbon is there, 3 hydrogens are there. So 3 alpha hydrogens are there. So it will show hyperconjugation, right? But we have to check for the compound in which hyperconjugation is absent. Okay, right. Next here, this is alpha carbon, but is there any hydrogen? Once look at this. Is there any hydrogen on this carbon? Is it having any hydrogen? No. Okay. So hyperconjugation is not present in this. Alpha hydrogen is hydrogens are present not on the alpha position. They are present on the beta. This is alpha on next carbon beta. This is alpha on next carbon beta. This is alpha on next carbon beta. Clear? On alpha carbon, hydrogens are not present. That's why hyperconjugation is absent there. Okay. Now, here, yes. This side 3 hydrogens, this side 3 hydrogens. Total 3 plus 3, 6 alpha hydrogens are there. Here, how many alpha hydrogens are there? This is carbocation, this is alpha position. Don't take this, only this one. Okay? So 2 alpha hydrogens are present. 2 alpha hydrogens are present. Clear? So answer is B. Okay? Let us take some cyclic compounds, cyclic carbocations. In which of the following same hyperconjugation is absent? This example is very, very important. Okay, right. A, B, C, right. In which hyperconjugation is absent? What is the condition for hyperconjugation? Presence of alpha hydrogen, right? See this carbon with positive is carbocation, this dot, okay? Carbon which is next to carbocation is called alpha carbon. This is alpha carbon, alpha position. First we have to find out alpha position in the cyclic examples. This is also alpha position, right? So we have 2 alpha positions here. Here alpha carbon, here also alpha carbon. Okay. And what about this? This is CH3, right? This is also alpha carbon, right? So we have how many alpha carbons here? 3 alpha carbons. 3 alpha carbons. Okay. Here, this pink color. Take this pink color. Alpha carbon and alpha carbon. Here, this is alpha carbon. This is CH3, like this. And this is alpha carbon. Yes, we have alpha carbons in every compound, but in which alpha carbon is attached to hydrogen, we have to check. Okay, I'll tell you one basic thing before starting this. Once look at this. We know carbon valency. For example, if I draw the skeletal structure like this, how to balance these carbons? This carbon is attached to how many bonds on the right side? Only one bond, but carbon valence is 4 now, so we have to write 3 more bonds. So what I'm writing, H here, H here and H here. Okay, and this carbon is connected to how many bonds? 1, 2, 3. 3 bonds are connected, so write one more hydrogen. And this carbon is connected to how many bonds? 2 bonds, right? See this carbon is connected to 2 bonds now, so 2 more hydrogens you have to keep here, like this. Clear? We know already how to balance the carbons. Okay, if you take one cyclic structure, each point of intersection represent carbons. Okay, this carbon is connected to how many bonds? This is one bond and this is one bond, 2 bonds. So 2 more bonds should be present now. So we have to keep 2 hydrogens here. You have to imagine 2 hydrogens. Similarly, this carbon also, this is connected to how many bonds? This is one bond and this is one bond. Okay, it is connected to, let us give numbering, then you can understand easily. Second carbon is connected to how many bonds? 1 and 2. But total valence is 4 now, so you have to imagine 2 more hydrogens here. This is basic concept. Clear? Right. See this example. You tell me, at this dot, how many hydrogens should be present? This pink color dot contains how many hydrogens? First of all, tell me that pink color carbon is connected to how many bonds? 1, 2, 3. 3 bonds, surrounded by 3 bonds. But carbon valence is 4 now. So you have to imagine 1 hydrogen there. Clear? See this example. Here pink color carbon contains how many hydrogens? Guess. How many hydrogens? 0 hydrogens. It is not containing any hydrogens. 0 hydrogens. Why? Because already it is surrounded by 4 bonds. How? See. 1, 2, 3, 4. Already this carbon is surrounded by 4 bonds. So you no need to write any hydrogen. So this carbon do not contain any hydrogen. Okay, we use this basic concept in the previous question. Clear? Right. Use the previous concept, basic concept and answer. First one. Okay, I am erasing these alpha positions to write hydrogens. Okay, let us start. This is carbocation. Next carbon is alpha. You tell me this carbon contains how many hydrogens? Just now explain now. This carbon is connected to how many bonds? 1, 2. Only 2 bonds. Okay. So 2 more hydrogens you have to imagine here. 2 hydrogens here. This is alpha carbon, so we have to check hydrogens at alpha carbon only. Carbon which is next to carbocation is alpha carbon. This carbon is alpha carbon. Why? This is connected to carbocation. Okay. Next. This one. This is also alpha only, not because this is connected to carbocation. This is alpha. It contains how many hydrogens? See, this is connected to, I am using another color. This is pink bond, this is pink bond. How many pink bonds? 2 pink bonds. So it is connected to two bonds, but carbon valence is 4 now. So you have to imagine two hydrogens. Here two hydrogens. So total how many alpha hydrogens are present? This is also alpha position only. Total how many alpha hydrogens are present in this? 4 alpha hydrogens. 4 alpha hydrogens. Clear? Now coming to this. Take different color. This violet carbon. This violet color carbon is connected to how many carbons? 3 carbons, right? This is one carbon, this is one carbon, and this is another carbon, red color. That are alpha carbons. This is carbocation alpha, alpha, and alpha. Okay, we have to check hydrogens at alpha carbon only. You tell me, based on our previous discussion, this red dot is connected to how many bonds? Below one bond, above one bond, 2 only. But carbon valence is 4. Now you have to imagine 2 hydrogens. Here also same, you have to imagine 2 hydrogens. Okay, here directly displaying 3 hydrogens are there. See, sometimes you will get like this only. You have to imagine CH3. Sometimes you will get single line like this. Okay, you have to imagine whenever you get single line, at the end you have to imagine CH3. Now it is CH3 only. So 3 alpha hydrogens here, 2 here, and 2 here. So total 3 plus 2, 5. 5 plus 2, 7. 7 alpha hydrogens. Okay, now look at this. This yellow dot. Now consider yellow dot as the carbocation. These pink carbons are alpha carbons. Now you tell me, is this pink carbon having any hydrogen? No. Why? Because this pink carbon is already surrounded by 4 bonds. 1, 2, 3, 4. So it is not having any alpha hydrogen. It is alpha position only, but it is not having any alpha hydrogens. Similarly, this also, this pink carbon is surrounded by 1, 2, 3, 4. Already it is surrounded by 4 bonds. So there is no alpha hydrogen. Alpha carbon is present, but there is no alpha hydrogen. So in this, hyperconjugation is absent. Here, how many alpha hydrogens are present? See, this terminal line, okay, represents CH3. You have to imagine CH3 here. Okay. Now you tell me, in second pink, at second pink, how many hydrogens are present? This carbon, pink carbon is surrounded by 1, 2, 3. Already 3 bonds are present. So one more hydrogen will be present. Imagine 1 alpha hydrogen. Here 3 alpha hydrogens. So totally 4 alpha hydrogens are present. But alpha hydrogens are present. Clear? So in this alpha hydrogens are not present. Clear? Right. Let us see the applications of hyperconjugation. Applications of hyperconjugation. See, by using hyperconjugation, we can predict the stability of carbocations, and we can predict the stability of alkenes, and we can predict the heat of hydrogenation of alkenes. See the applications. By using hyperconjugation, we can predict stability of carbocations, stability of alkenes. The one and only electron displacement which is used to predict the stability of alkenes is hyperconjugation only. Okay, and heat of hydrogenation. Okay, first let us discuss stability of carbocations. Okay, right. Stability of carbocations. Stability is directly proportional to number of alpha hydrogens. You know how to find alpha hydrogens. Clear? If more is the number of alpha hydrogens, more will be the stability. Okay, let us see one question. Identify stable carbocation. Identify stable carbocation from the given below. Okay. Same example I will given. Before that I given this example only, right? Which is having more number of alpha hydrogens. Right, directly we know how to write alpha hydrogens. Here 3 alpha hydrogens are present. Here, see, this is alpha carbon only, but where is hydrogen? It is not connected to hydrogen directly. Okay, this is alpha carbon. This is alpha carbon. See, is there any hydrogen on it? No. So 0 alpha hydrogen, so 0 hyperconjugative structures. There is no hyperconjugation. Clear? This is having how many alpha hydrogens? This side 3, this side 3, so 6 alpha hydrogens. This is having how many alpha hydrogens? This is alpha position, 2 alpha positions. So which is having more number of alpha hydrogens? C. So C is more stable. C is more stable. Okay, right. Next, another example. Second example. A and B, which is more stable, which is having more number of alpha hydrogens. See, this is alpha position, this is alpha position, this is alpha position. Okay, here 2 alpha hydrogens are present, here 2 alpha hydrogens are present, here 3, because terminal dot represents CH3, 3 alpha hydrogens. Okay, so total how many? 2 plus 2, 4, 4 plus 3, 7 alpha hydrogens are present. Okay, next, here this is alpha position, this is alpha position. At this alpha position, how many hydrogens are present? 2 hydrogens are present. At this, how many hydrogen? 1 hydrogen only. Why 1 hydrogen? Already this dot is surrounded by how many bonds? 1, 2, 3. Already 3 bonds are present. Okay, so you have to write 1 hydrogen. So 1 alpha hydrogen is present. So total how many? 3 alpha hydrogens are present. Clear? 7 alpha hydrogens are present. So first one is stable. A is stable. Clear? Okay. See, one important information, when resonance is present and hyperconjugation is present, which will get priority. For example, in one compound resonance is present, in another compound hyperconjugation is present, then which electronic effect we taken into consideration? We take into consideration to predict the stability. That is very, very important. See, I am giving that point under note. While predicting the stability of carbocations, first give priority for resonance. Okay, then give the priority for hyperconjugation. First resonance will get priority, then hyperconjugation. After that, inductive effect. I stands for inductive effect. Okay,